the area of a sector, which is like a slice of pizza. We call that a sector. So when we subtracted the triangle to get the little slither we call the segment, we were using a sector area of the circle and then subtracting a triangle area. That's what we were really doing. Now, the arc is the distance along the circumference, and that's called arc length. Now, you can use proportions for these, and a lot of times that might actually be easier. There are formulas, okay? But if you use these two formulas, you have to use radians, and I'm going to show you why in a minute. And so I'm going to symbolize the radians with this theta symbol. It's a circle with a horizontal line that's called theta. It's a Greek letter. So the Greek alphabet, it's one of those ancient languages that still lingers because we use it in mathematical symbols. This is called theta. Okay, so that's what that is. All right, so the ratio of radians is to 2 pi, as the central angle is to 360, as the arc length is the total circumference, as the sector area is to the total area. So all these are proportional. Okay, so I'll do a couple examples in a minute, but let me show you where these formulas came from. These formulas came by taking the ratio of radians to 2 pi and putting equal to these two ratios over here. That's where those formulas came from. So if you write radians, I'm going to use the capital letter R, and I'll show you what I'm doing in a minute. And we're talking about the arc length. So I'll use the little letter L, and then 2 pi, and I'll use a lowercase r just to be different. Well, let me not make this so complicated. Well, I have 2 r's in the problem, so let me just put the theta symbol there. Yeah. And I'm just going to do something stupid. All right, so here's our proportion. The arc length is the total circumference, as the radians, which I'm using the letter theta, is the 2 pi. Okay, now notice because you got 2 pi's on the bottom, you can multiply both sides by 2 pi. And now when you cross multiply, you get this. This is why we use radians. Every circle is a multiple of a radius 1 circle, right? Remember we're looking at when we had a radius 1 circle and a radius 10 circle was 10 times bigger. So we multiplied the radians to the radius. That's another way to think about that formula, but mathematically, this is where that comes from. All right, so this has to be radians because that's where we derive the formula from. The formula was derived by using the radians ratio, not the degrees ratio. And if you use the degrees ratio, you won't be able to cancel the 2 pi. That's why we were able to simplify this. So you can use the proportion to central angle of 360, but you're going to still have pi in your answer. Whereas if you use radians, you'll be able to cancel the 2 pi. Okay, so now the second formula, the sector area, it comes by the same technique. Okay, so we'll take the radians to 2 pi ratio. We'll put that equal to the sector area as a ratio to the total area of the circle. So I'm going to use the letter A for the area. All right, now again, both of these symbols has a pi in it, but now you don't have a 2 pi that's going to cancel. So if you multiply both sides by pi, you get this. And now multiply by r squared. Okay, so that's where the formulas come from. They come from simplifying the proportion that you can set up using the two ratios. And when we say proportional, this is what we mean. Two ratios are equivalent. That's called proportional. Yeah, maybe you know that. I don't know. All right, so now let's have some examples of this. All right, so let's say that we had a circle and we were told that the radius was 3. Let's find the area of that sector and the arc length of that sector if we're told that the central angle is, let's just say 30 degrees. All right, well, we got degrees here, so we might as well use the proportion based upon 360. So 30 is to 360 as the area is to pi over 3 squared. Solve that. Or 30 over 360 is equal to the length as 2 pi times 3. Now I'm going to assume you know how to solve those equations. All right. All right, now what if we wanted to use radians? Okay, so if we had a situation where we were given radians instead, so let's say we had something like this, and let's say this is a radius 4 circle, and we're told that the central angle here in radians would be, let's say, 2 pi over 3. Well, if you're given radians, you might as well use these formulas, right? Okay, so then this is 4 times bigger than a unit circle. So 4 times 2 pi over 3 would be the length. And the area, go ahead and use this one. Now, again, I'm going to assume that, you can solve that. That's, it's just, I don't even know if I'd call that algebra. All right, now let's go the other way around. Let's say you're given the area of a sector and you want to use the area of the sector and the radius to find the central angle, or you're given the arc length of a sector and you want to use that with the radius to find the angle, or you could use the area and the arc length with the theta to find the radius. So depending on what you want to find, because there's 3 variables here: arc length, area. When I say 3 variables, 4 variables: radius and theta. All right, so let's say that we know that this area is 10 feet squared. All right. Now, what we do next depends on if you want to use radians or you want to use degrees. Because if you use radians, then you can use this formula. All right, let's go ahead and just use degrees for the sake of it, though. So what would be the degrees? All right, well, if we set up a proportion, so theta, and I'm using theta loosely here, okay? So we're looking for degrees to 360 equals, well, we know the area of the sector is 10, and so we just solved that. So basically multiply by 360 to this fraction. Okay, now what if we, instead, we're told that the length of the arc was 11 feet. All right, now let's go ahead and find radius. All right, well, we can use this one. All right, okay, so then 11 equals the 3 times theta. So notice 11 over 3 would be the radians. Okay, now radians is just a number. So sometimes it might have a pi in it, but it doesn't have to have a pi because you could multiply 2 times the pi divided by 3 to get a real number. So don't get into the misconception that this has to have a pi in it. It doesn't. If the numerical values that you're using in the formula don't have a pi, then you're not going to get a pi here. All right. So the last little thing here, what if we wanted to find the radius based upon some given information? Okay. So let's say same kind of thing. Let's say now we have the area given to us, and I'll just say 50 inches squared just for the sake of it. That might be a little unrealistic. That's going to probably be bigger than the circle. Let's be a little more realistic. So I'll just say the same thing, 10, just to keep it simple, right? Okay, and let's say that we don't know what the radius is, but we know that the radian measurement was pi over 3. So I'm just making up a number. All right, well, what would the radius be? All right, well, we're going to use this formula. Again, we have radians. Okay, so then 1/2 times pi over 3 r squared equals 10. Now this one I'll solve a little bit more because it's a little more involved. Okay, so then you'll have pi over 6 radius squared equals to 10. And then you multiply the reciprocal, so this becomes 60 over pi, and then you take the square root.